Okay, so as I mentioned, one of the questions that comes up in data analyses is, what statistical test do we use? Let's assume we have found some data, because the answer to the question, what statistical test do I use, depends on primarily the data at hand. It doesn't matter what you hypothesize, you can't do anything without the data first. That's why from this paper, which I will pin to the class discussion board, we start off thinking about the data structure. And here we're talking about interval data, which is another term for numeric data. So think of the data first. Think about, what do I have? What is the raw material I can use to make a statement, to test a claim? If you don't have numerical data, you cannot do the types of tests that we have below. But if you have numerical data, then and that is your primary interest, then you can do a couple things with it, given our knowledge in class. So interval here, of course, as I mentioned before, it means numerical data. You'll often see in practice different terms, but numerical and categorical is, I think, the most useful distinction. Language here is also a little confusing because they talk about hypotheses of difference. I don't want to emphasize that because it's just redundant. Think about whether or not, if your primary focus in the data set is a numerical variable or numerical variables, it need not be those need not be the only numerical variables in the data sets, and other variables in the data set can also be categorical. You'll probably come up with many more variables than you can analyze. But if you're interested in, say, income, I gave a hypothetical example. I'm interested in income. I'm interested in, and I could be interested in many aspects of income as a variable. If I were interested in looking at an association of income with another numerical variable, then I would do a correlation coefficient. Now, what they don't include here is they say greater or 2 measures. If I were interested in prediction, you could use correlation, but you can also use simple linear regression. The reason he writes multiple regression is, in practice, we almost always use multiple regression, but that is really just a simple extension of simple linear regression. You actually already know multiple regression. So the distinction here is 2 measures by themselves, or 2 measures where you want to predict an outcome. So for example, 2 measures, so association predicting outcome of interest. This was an issue in the midterm, if you recall. Some students had gotten a question, I believe it was question 17, reversed because the wording talked about predicting an outcome. That's because in regression, it is not standardized. The slope coefficient and the intercept are all measured in terms of the outcome variable y. So if we wanted to, say, predict height of professors, height in centimeters, and their salary in dollars, we could do a scatter plot, just as we would for the association for Pearson's R correlation. And with Pearson's R correlation, we would come up with a correlation coefficient, and we would interpret that. With simple linear regression, if our interest is on salary as an outcome, because we hypothesize that taller professors are more highly valued and shorter professors are discriminated against for no other reason because then they're shorter, then we would hypothesize a positive association, and we would look at what happens to a professor's income as they increase by 1 unit in in our measure of height. So these are both different frameworks for interpreting the outcome. The difference is R is often more preferable and more widely used, not only because it is flexible, as I've told some students, but because it also measures an outcome of interest. And almost always, even I automatically think of regression, simple linear regression, as actually a special case of what is really multiple regression. And that's in the course, Student's Guide to R if you're interested. But all multiple regression does is it gets rid of the confounders that can occur if we only look at correlation. Remember when we talked about spurious correlations? And I posted that to the discussion board. Some of you had a good laugh at this, because you can find any kind of spurious correlation. Well, spurious correlations exist because we're not adjusting for or accounting for the fact that there are other contributions to the fact that, say, some professors, taller professors, might earn more. Is it the case that taller professors earn more because men are more likely to be tall? Or is it because taller professors, regardless of gender, earn more? Well, we wouldn't be able to test that fact with simple linear regression, and that's okay. But I'm just telling you that's the method that you would come up with. We talked about hypotheses of difference. When we talk about difference here, think about, okay, I'm interested in income, but am I interested in a difference between two groups, right? So two measures. Am I interested, say, in the difference between let's say I'm looking at professorial income, and the Secretary of Education believes that professors are way overpaid on average. And I have a sample of professors of income, and I'm going to test the difference between the hypothesized mu, or the hypothesized value mean in the population, versus my sample population mean. And that is a one sample t-test. And we learned about that in the previous week. And that is actually a hypothesis of difference, because you have a hypothesis of a population measure of the population mean, and then you have the sample mean. And you want to test whether the sample mean is consistent with the population mean. I can tell you on average, the person who would say that professors on average are paid $200,000, if the Secretary of Education were to say that, that is not true on average. It's true in some institutions, but not on average. It's not a normal distribution. Now, as I said in the section, that's a less common than a one sample hypothesis test is often less common to see in published papers than a hypothesis of difference between two groups in the sample or over time, maybe before and after a treatment. Say you're given a drug and we want to see, let's say you're in an experiment, we want to see whether or not, how do I put it, depression is diminished, depression scores are diminished after people take an antidepressant. Well, in the experimental group, you might take the antidepressant and you might compare the group before and after. That's what they call a sample selection dependent measure, but we don't really look at that in the class. This is like a pre and post test. I don't think we even have any examples. So you might not want to think about these pre and post test examples, but that's what they call the paired t-test. What we're really interested in is going to be this right here, where we have our two measures, and our sample selection is independent in the sense that we have two groups that we're not measuring the same person before and after a treatment, which means that you know, my sample selection is dependent on me. Instead, you're comparing independent observations. This is what this person is trying to say. You're comparing independent observations and looking at the difference in the averages or the means. This would be a two-sample two-sampled t-test. It can be one-sided or two-sided. So in my example, I would be interested in looking at whether or not professor incomes differ between men and women, male and female professors. And I would hypothesize that male professors earn more than female professors. And I would test that hypothesis. It would be a one-sided test of a difference in two means. You could also do a two-sided test. You might say there's just a difference between them. We often do two-sided tests more commonly. Now, I circled that test, that t-test here. You can cross out independent because it's a little confusing. And I circled R because we basically have simple linear regression. We have correlation. We have Pearson's R correlation. It's named after him. We have the t-test, which is named after Gossett, which we talked about. We have this F-test, which I mentioned at the beginning of the section, named after R.A. Fisher, right? This is not obligatory for the course, but it is relevant for those of you who might have more than 3 groups. So maybe you have professors who identify as male, female, and then maybe are not identifying with either group, a non-binary category, let's just say. Then you'd have 3 categories. Well, then your test is no longer a difference between 2 means. It is much more like what we're doing in the chi-square test, which is, are these means different from each other overall? It's what I call an omnibus test. It's an overall test of differences. So we could test whether or not non-binary male and female gender identities of professors vary by income. But we cannot conclude which of those differences actually are the cause of that income. We can only say that those 3 categories differ. So it's a weaker conclusion for the F-test. The only reason I mention that is that it is in the course, and some of you are looking at it, but it is not at all required. Now I want to emphasize, of course, you start off with the data here. You do have an interest, but sometimes that interest might be data-driven. I would be interested in salaries of professors and income because I believe there is a big difference in salaries between male and female professors. And I would be interested in looking at it because I think gender inequality is a huge problem we have in academia, especially in quantitative fields such as statistics. And that would be my motivation. And then I would look at the data and see what I have available. And maybe I don't have measures of height, so I can't do a more advanced multiple regression. But maybe I don't even have, maybe I have gender, but it's only 2 categories, things like that. Now, that's basically how you decide a test. Data, basically a general idea of what you're looking at, and then the tests that we have available, which is really t-tests, correlations, and regressions. That's what we're going to do for numerical data. I hope that was helpful. I said I was going to go a little bit over. It's basically the same kind of logic with categorical data. But again, this is the primary focus. So let me do a new share. And I'm going to share the other slide of this article, which I recommend you read, not because it is the best written, but it is actually better than others that I've seen. We won't have time, by the way, unless you can indulge me, we won't have that much time, but there are some online question and answer quizzes that will guide you, but I think those are problematic because they might take you in the wrong direction, but I'll still show them. This is much more useful because you get to see the overall picture. Oh, I'm sorry. I need to do a new share, which is going to be the other chart. Are there any questions about this procedure? I would argue that it's not the only procedure, nor the best, but it is what we do. You kind of deal with the cards that you've got, basically. And we have this in view now. Just want to make sure this is correct. Yeah, okay. So yeah, when we talk about when our primary interest is categorical, they're gonna actually, so this is an interesting issue, and I think it's a great example of some of the ways in which statistics is limited by certain fields. So a test of difference in proportions is very much like the two sample t-test. I think it's a close cousin. But notice here, the only one that they let us deal with here is, we don't even have that. The only example they give us is this chi-square test, which is a hypothesis of difference for two or more measures. Say you have a 2x2 table, and you want to look at the differences between those cell categories. So for example, revisiting our week on probability, is being poor, are poor people more likely, is being poor independent with, how to put it, is being poor independent with feeling depressed. And the chi-square test is like the analysis F test or analysis of variance. It is an overall test of the difference in the 2x2 table, the contingency table, that says at least one of these 4 categories in a 2x2 table is different than the others, but it does not tell us which one. Now I'm going to add a branch here because they do not recognize something else here. And what is this? Well, in fact, we do have a test of 2 measures, and that is the test that is the test of proportions of the difference in 2 proportions, or the proportion of 2 differences. The reason it is, I think, less common is because most often researchers are going to use the chi-square test, even if there are just two measures that are different. Because the chi-square test is flexible. It can use any number of categories. Same with the analysis of variance. It's an overall test that says, okay, compared to what we might expect, these cells in the 2x2 table, or the 2x3 table, or the 1x2 table, compared to what we might expect these proportions to be, are these proportions different than what we would expect? That's all that it says. That's different than the proportion test that I'm going to add in the text here, which basically says, right, sort of what is it, we're going to say 2 measures. The font is huge, but you know what I'm getting at here. The point is, we actually have one test in our toolkit that is not available. As I said before, that's often also because of the stats packages. I think this was written by a psychologist, and a lot of psychologists will tend to use the chi-square test, or this other thing, the coefficient of contingency called phi. Like use Greek symbols. It's a lot of this is disciplinary specific, but we're going to be able to add to this a proportion test, 2 differences. Right. So if I can do the text here, right? This is going to be the same as we've done, same thinking as we do in the t-test. We have 2 proportions. Maybe you have the proportions of, so for example, let's say we're just in professors again, and we're interested to see whether or not the proportion of female professors, of tenured female professors, is is greater or less than, or is different than the proportion of male tenured professors. Right, so this is a prop test function, difference in of proportions. You might also do another kind of test. You might have someone say, oh, the proportion of female professors is greater than the proportion of male professors who are tenured. It's 0.60. Well, then you can use a one sample proportion test to see against that claim. However, in practice, we're often looking at differences between groups. So again, we have that option that is not available when we have a difference in proportions between two groups. That's the proportional test. Now, the advantage, of course, is we can also add that chi-square test if we wanted to on top of it. It's not that informative, I think, because the chi-square test, as I've said, just as the F-test, is not that informative. So we do see some similarities here that the author is trying to draw here, which is first, we have a test of difference. We have a t-test and a proportion test. I'm gonna do my video because I'm kind of doing a little gesticulating here. So we have kind of three families of tests here. Oh well. Do you see me? Okay, yeah, good. We basically have three families of tests. We have two types of data that lead to two different kinds of hypotheses or analytic orientations, right? And then each of those have about three tests that we can look at. So either we have a numerical or categorical data at the center of our analysis. That is, we're either interested in something categorical or something numerical, such as income, categorical, such as the percentage of female professors who are tenured or the proportion of female professors who are tenured, as opposed to a numerical variable answering the same question or similar question about male-female disadvantage in academia, which would be, is the average income different between male and female professors? And you could test those differences in terms of a difference between two groups. And if it's a difference in two groups, you do a t-test if it's income, and you do a proportional test if it deals with a percentage or proportion. You would do, if you have more than two groups and you want to look at the differences, then you would do a less conclusive overall test of the difference among two or more groups. And you're just essentially testing this hypothesis. Are the groups the same, or are they different than what we would expect? So do they differ from what we would expect them to be, given, say, the prevalence in the sample or something like that? So for example, for male and female professors, a chi-square test of differences can be used for two categories, but it's more useful if you say you have three or more categories and you want to see, okay, do these groups differ at all? And that's the omnibus test, but then it doesn't tell you which category is greater or lesser than which category is driving the group. So if you have three categories in the chi-square test, looking at interval data or looking at categorical data, and proportions of tenure rates, it could be that the chi-square test is significant because the three groups differ, but only because men are more likely to be tenured than both non-binary identity, gender identities, and those who identify as female. That could be the difference. Or it could be or you could have a chi-square test that is significant because females who identify earn less than both binary, non-binary and male groups. You just don't know. There's a post-hoc test, but those are real problems because then you're just fishing for results. We don't have a measure of association when we look at categorical data, but it does exist. Now we look at numerical data, we have more options. We can look at the t-test, which we talked about, and we can look at, if we're looking at association, we're just looking at, is there linear association? We look at correlations, which give us a standard measure. So if we want to compare different kinds of outcomes, again, correlation works. But if you want to look at one outcome and predict that, regression is going to be better because regression is expressed in units of the outcome. So we're looking at income as the outcome and male and female status as the predictor. Then the slope of the line is going to be expressed in income. The intercept, that is the value of the slope of the line, regression line, when x equals 0, is going to be also expressed in income. And you're going to predict income values. Correlations are useful, however, if you want to compare across different groups. Maybe you want to compare the correlation of the percentage of women in a discipline, academic discipline, and the years until they get tenure in the discipline. And you would argue that it takes longer for women in female-dominated profession disciplines. Maybe it takes them longer to get tenure. You could look at, and that would be a correlation coefficient that's standardized. And you could look at another part of the data set and say, okay, now we have the correlation between percentage of female in the discipline and the percentage of Title IX reports of discrimination at the university or within the discipline. That's a different outcome, different measure, but here you have two measures that then are standardized because the correlation coefficient can compare across groups. That's how I would choose the data sample, obviously the data analysis. And I know a couple of you are leaving, rightly so, and this will be recorded. I just want to end on exploring a little tool that I have on. Well, you know what I'll do? I'll just post the links on the course website. But there are a couple of sites where you can actually click the types of data projects and analyses, and it'll kind of guide you through. It's like a choose your own adventure or kind of role-playing game, but it doesn't tell you in advance whether or not you're able to do the procedure involved. Anyway, I hope this was useful. I hope it's encouraging at least. If you have any more questions, thank you very much. But I hope this answered some questions. Have a great night, and if you have any questions, please let me know.